All right, so I'll introduce myself. I mean, you can involve, but that's it.
It's a pleasure to have that Colbrook on in town ground here.
Yeah, I've been to the I-9 so many times, but it's fun. So I'm going to be talking about computing spectral properties of Kuban operators. And this talk is going to be, the series of talks are going to be a little bit strange because I'm sort of sat somewhere in the middle between applications and pure mathematics and rigor. So I just want to reassure those in the audience who love theorems and proofs. Everything I'm going to talk about can be made completely rigorous. I'll give you a reference to a book at the end of the series that does this comprehensively. And those of you who are the other side and love applications, there'll be a few pictures, perhaps not in as much detail as you want, but again, you can look at the papers and you can find the details. So hopefully the idea of these talks is to give you sort of the high-level overview or ideas that allow you to compute spectral properties of Kuban operators. So let me first give you the setup. So we'll be working on some typically compact metric space. You can often drop the compact. So this is the state space. And you have a continuous function f that governs a discrete time dynamical system. Okay, so I'm not throwing in any noise or anything like that at the moment. So the state of n plus time n plus 1 is f state of time x. This is sort of the classical viewpoint. And then you move into the 20th century and you start using analysis. Okay, so you stick a Borel measure on the space, and then it's sort of classically you'd look at an L2 space of observables. Okay, so there's been some hints about the space and stuff throughout the talks. So for the time being, we're going to stick to L2. In the final lecture, we're going to look at different Hilbert spaces. And what you do is you look at this Kuban operator. Okay, so this is just an operator from L2 to L2 defined by this pointwise definition. Again, some notes for those of you who like functional analysis. I like functional analysis. This is a pointwise definition. L2, of course, is an equivalence class of functions. So you have to have some conditions that make this well defined. So we'll be assuming that these hold throughout the talk. If you're on the application side and you don't care about this, just ignore. Okay, so we've got 19th century, 20th century. We move into the 21st century, and we're all crazy about data. Right? So the goal is to learn something about this f. Typically, it might be unknown or too complicated to study from snapshot data. So all snapshot data are pairs, okay, x and y. So y is just sampling of f, right? So you've got samples of f. It might come from a single long trajectory or might come from multiple short trajectories. I'll get on to how those assumptions come into play in a little bit. Okay, so this is sort of just to set up the notation. So this Kuban operator on this L2 space. So the goal of this series is to compute spectral properties. And perhaps I'm too greedy, but I like rigor and I also like practice. Okay, this is what I was saying about being in the middle. So the first lecture, we're going to compute spectra. The second lecture, we're going to deal with continuous spectra and spectral measures. I'm going to show you how to compute them. And then in the third lecture, we're going to start thinking about actually how hard are these, right? Can we classify their difficulty? And in fact, can we build adversarial dynamical systems to show that some things are impossible to compute? And we're also going to go to, rather than L2 spaces, reproducing Hilbert spaces. Okay, so this is where a lot of current Kuban work is happening. Okay, so a lot of what I can say, a lot of what I'm going to talk about extends beyond just Kuban. Okay, so the principles can be applied typically to closed operators on a separable Hilbert space. Again, if you don't know what those words mean, just people. Okay, so we have this goal, compute the spectral properties. And before launching into this, you probably want to know why. Why do I care about the spectral properties of this Kuban operator? So here's one example. So suppose you have what's called a pseudo-eigenfunction. Okay, so this is your L2 norm. G, I'm assuming, is a normalized observable. And it's almost an eigenfunction with eigenvalue lambda. Okay, you've relaxed this equality to some epsilon. Okay, some positive epsilon. Then, assuming certain properties of K, like it's norm 1 and things like that, if you observe this observable n time steps in the future, this is the same thing as applying multiplication of the almost eigenvalue n times plus some remainder. So in this remainder here, there are two things to note. As n gets larger, it gets larger. As epsilon gets smaller, it gets smaller. So if we can find a good candidate here with small epsilon, we can get what I call coherent features. Probably not the same thing that other people in the transfer operator call coherent features. I never really know what this word means. So excuse me if it's clashing with your understanding. But the point is that even for chaotic systems like this, you can get these patterns. Okay, so this is an observable with a very small epsilon. It's actually a smooth approximation of what's called a generalized eigenfunction, which we'll get on to in lecture 2. And so you're seeing the observable, the color is the value, and then in time it sort of oscillates. This is like the square of this, and this is the square of this. So you can start to see these nice behaviors. And we can package all of this into this set here. Okay, so let me I also wrote this definition here. The spectrum of an operator A is all Z in C. So this resolvent A might say I inverse does not exist. And what you can do is you can relax that assumption. So one of the things we're going to use is that this resolvent allows us to compute spectra. So there's something called the approximate points pseudo spectrum. This set here, spectrum epsilon. It's all Z in C such that there exists a G of norm 1 where you have this equation. Okay, so you've got like an epsilon relaxation of, I guess I should call it the approximate point spectrum, which might be inaccurate thinking about the spectrum. Okay, so this set sort of gives you where you might expect this coherent behavior. And the idea is that Koopman is trading a nonlinear, typically finite dimensional system for a linear, infinite dimensional object. Okay, so we go back here. Unless you're in kind of trivial situations, this space is infinite dimensional. So you're going to have to cope with that infinite dimensions, particularly if you want to capture nonlinearity. Okay. Why as well? So here's some other stuff. So this is a fundamental object in ergodic theory. So Steve touched on that in his lecture, the ergodic theorems. Okay. You can also get spectral expansions, kind of stuff Beagle is talking about as well. So this is an example for unitary Koopman operators. You can measure preserving invertible systems. It's expansion of an observable in terms of eigenfunctions, and then generalized eigenfunctions or an integral over a continuous spectrum. And then you can evolve it, right? So you can get this power of the eigenvalue and then this sort of Fourier type behavior over the continuous. So the point is that you can get things like prediction. Okay, and as we've been seeing, the spectral properties also encode geometric features and a whole bunch of other stuff. Okay, and there's a huge amount of interest in computing their spectral properties. A fun graph that I gave up plotting in 2021. So this was when I first got into Koopman during COVID. I had too much time, so I tracked the number of papers, and there was an explosion. I should probably update it because I expect it just continues. Or maybe during COVID, everybody's writing papers about Koopman and stuff, I don't know. But there's a lot of interest, typically in applications. Okay, so here's some survey articles. So I will put up my slides on my website. I realize I'm going probably too fast through this introduction because I want to get to the proper stuff. But if you want any of the references, just either email me or look at my website. Okay, so there's a Sign Review article in 22 that's a really good sort of synthesis of what was known at that point. And then there's this fun paper. I was watching too many Marvel movies, so I called it the multiverse of dynamic mode decomposition algorithms. And then I got wary of Marvel movies like everybody else. Perhaps I wouldn't call it that nowadays. But anyway, we'll see lots of dynamic mode decomposition algorithms throughout these lectures. This is sort of like a numerical analysis perspective on those algorithms. Okay, but here's the caveat. So although there's tons of applications, so I would probably say, it's probably fair to say 90, 95, 99% of these papers are just taking an algorithm off the shelf and applying it, right? And I'm not meaning that in sort of a negative way, but there is a gap, which a few of us are trying to fill, which is convergence guarantees of verification. Okay, so there's a few people in the room who've done really good work on that. But why is there this gap? Why out of all of these papers are there very few on sort of rigorous guarantees? Perhaps it's a different community with different focus, I don't know. And this is part of the point of this I&I program, is to get people mixing together and talking to each other. But also, dealing with infinite dimensions is really hard. So hard, in fact, that it's given me a job, right? This has been something that I've loved over the last few years. And if it wasn't hard, I'm not sure I'd have a job. Okay, so here's an example on L2Z, or Z, sorry. This is a really nice operator. Okay, so L2Z, what is this? This is like you can think of it as the space of Fourier coefficients of L2 periodic functions. Okay, what is this infinite two-way matrix doing? Is it's shifting back those coefficients. Okay, so two-way infinite Jordan block. It's unitary. It's a really nice operator. Its spectrum is the unit circle. Okay, so that's that over there. Spectrum is stable. Here's something interesting. So in finite dimensions, of course, you can characterize this in terms of the determinant, and you only have eigenvalues. This operator doesn't have any eigenvalues. Okay, so if you try and write down the eigenvalue equation, and you look at the eigenfunction, you quickly get something that's not normalizable in L2Z. Okay, and this corresponds to unitary evolution. Right, so when I give you an infinite operator or a Koopman operator, the first thing, if you want to compute its spectral properties, you think of is probably to truncate it to some finite dimensional approximation and compute eigenvalues, right? You do that for this, you get the Jordan block, the bad guy of numerical linear algebra. Okay, this is a beast. This is horrible. Spectrum is just zero, right? Look at the diagonal to see that. The spectrum is unstable, exponentially so in the truncation parameter. It's discrete spectra, but also the algebraic multiplicity stuff. And it corresponds to Nilkerton evolution. Okay, so if you raise this to the power of n, you get zero. So you've taken this infinite dimensional thing, you've truncated it, and you've broken all of the nice spectral properties, right? And the issue is that lots of Koopman operators are built up, well, okay, they kind of behave a bit like this. Okay? Sort of shift operators. So what we're going to try and do throughout this lecture is fix this picture. Okay, how do we fix this picture? Because when you're doing anything DMD related, so DMD, EDMD, you're always in the background doing this step. Okay, going from an infinite dimensional Koopman operator to a finite dimensional matrix by projecting onto a subspace of observables. And it turns out that there's some simple tricks you can do to get rid of this annoying behavior. Okay, so that introduces us to the first lecture. So what we're going to do is take a road from DMD through to res DMD. Okay, and along the way, I'm hopefully going to convey to you that the way to view EDMD, so that's extended dynamic mode decomposition, is really as a Galerkin approximation. Okay, so for those of you who've seen finite element methods, it's essentially the same thing, but for a Koopman operator, and where you're using data to get the integrals, the inner products. Okay, so any questions before I launch into the meeting? All right, good. Do shout out, right? Okay, so what is extended dynamic mode decomposition? So how do we connect this algorithm to Koopman operator? Okay, so I've got some references here. So you have the two key DMD references, and then this EDMD reference. This was I think the paper I read during COVID, where it kind of clicked for me, right? I struggled to understand DMD until this viewpoint sort of hit it with a transpose. We'll see that in a second. So what does EDMD do? So you have this operator acting on this L2 space, okay? You pick a bunch of functions or observables, these basis functions. People also call it a dictionary. So psi j, so a finite number, j equals 1 to n. And to build a approximation of the Koopman operator, okay, think finite elements if you've seen that before, you need two types of inner products or correlations. Okay, so the first is the inner product between the basis functions themselves. The second is where you have this Koopman operator k here on the left. Now remember, all we have access to are these snapshot data. Okay, so x blue, y in green. So what you can do, and this is exactly the viewpoint these guys had, an ingenious step, I think, is to treat these points as quadrature points for an integral. Okay, so you do that, and then you have some weights. I'll talk about these weights in a second. So you can approximate these two inner products via these sums. Okay, so just an approximation of an integral. And you work through the algebra, and then out pops this sort of matrix representation. You have psi x, this blue matrix, which is just the dictionary evaluating the x points. And then you have this diagonal weight. Okay. So that's the first in the product. Now, if you want the Koopman operator here, remember the Koopman operator acts as composition with f. But y is f of x. Okay, so you just trade this blue guy for a green guy. Okay, this blue matrix for a green matrix, so y, and out pops your approximation of the Koopman operator. Okay, so you're doing this truncation step we had before when we were going from the shift to the Jordan block. You just have to take this inverse here to account for the fact that this might not be an orthonormal basis. Okay? A few little things. If you want to compute the eigenvalues of this, often it's not a good idea to apply the inverse. You do a generalized eigenvalue problem. There's lots of numerical linear algebra tricks behind this. If you want to know more, talk to Zlatko, who I think is here somewhere, but he's really... I saw him maybe yesterday, but maybe it's something. But yeah, so he'll be here at some point in the program. So chat to him about the conditioning and things like that. He's really taking that forward. Okay, so we have this finite approximation of the Koopman operator. Before moving on, let me just say a word about these weights, how you might pick them. So there's typically three scenarios. Okay, so for example, suppose we want to approximate this in a product. Okay, we want this to converge as we collect more and more data. The first is pretty unrealistic, unless you've got a small dimensional simple system and you've got lots of freedom. You might pick these to be a high order quadruple. Okay, this can lead to very rapid convergence, but it's restricted. Okay, so think of, imagine you've got an interval, equispace points are terrible, right? You might do like some Gauss quadrature or something like that. The other one is random sampling. So you should think of this as short trajectories, short bursts. Okay, so this is sort of Monte Carlo. This is pretty good for large dimensions. Typically, although not all the time, you have an inverse square root rate of convergence. The other one, which is probably the most common in Koopman applications, is where you have a single long trajectory and you assume some sort of ergodicity. Okay, and there x and y are connected like this. Okay, so xm plus 1 is f of xm. This is also good for large dimensions. The convergence can be arbitrarily slow. There are tricks to speed up the convergence. For example, you can use tapering. So we had a recent paper that does that, but that's not really the story of this talk. So there are sort of three regimes where you can think of this as a good approximation. But of course, we always have a finite amount of data. Okay, so we can never really truly go to infinity unless we have some sort of analytic representation of this integral. Okay. So exercise, yes. So this is where I moved to the board. This is telling me to move to the board. So we have this EDMD matrix. So what's the connection with DMD, right? Why is extended DMD an extension of DMD? Well, if you take and this is something to do, particularly if you're a student and you have a good brain for these things still. What you can do is you can take, these are the POD modes that Steve was talking about in DMD. You take the adjoint and you apply it to the state space X. So now I'm assuming, sorry, the state vector X. I'm assuming that my state space is some subset of RD. Then, if you're thinking of this as a function, okay, the matrix that you get out from DMD is the transpose of the EDMD matrix. Okay, so K E DMD is equal to K DMD. So it's not quite correct to say that DMD is a Galerkin approximation of the Koopman operator. You have to be a bit careful. So another way of thinking about it, okay, is that
what were the psi? So far, what were the psi functions?
This is my choice of basis. Sorry. So if I apply DMD with the choice of linear basis functions, I get an EDMD matrix, which is the sign. Yeah. My writing is terrible because I don't like so much about.
And the U is what?
The U are the POD vectors, right? That you get from DMD. So remember DMD, you're doing this SVD, you get back the U's. Yeah, so this is the jth column of the U matrix. So DMD is the transpose of EDMD with a linear choice of basis functions. Okay, and this should already tell you that something's a bit suspect, right? How can you possibly capture nonlinear effects with a linear basis? Okay, that's fundamentally a limitation of DMD if you use it like this. So really, you have to go to EDMD if you want to get the true connection with the Koopman operator. Any questions on that connection? No? Okay. Either that means I'm really clear or everybody's really tired.
So maybe
Yes, yeah. Excellent.
So you say, how do you expect to capture nonlinear, but Koopman is linear, right?
But on an infinite dimensional space, that's the point, with nonlinear observables. So my point is, if you're projecting onto a subspace of linear observables, you can't do it. So you have to do EDMD, and actually you have to do EDMD with an increasing basis, right? It's a sequence of subspaces that fill out the Hilbert space. So we'll get to the convergence of that in a second. Yeah.
Just a little comment.
Yeah, please.
There is a bit of confusion. If you go to, and you know this, but maybe it's useful. If you go to Lorentz and you just do X, Y, Z, of course you're going to get crap, right? Because Lorentz is not a linear system in your finite dimension. But if you go to something like a fluid flow, and you're taking, a massive number of observables, which is velocity.
This is still a very big space. Yeah.
Yeah. So now let's suppose that your dynamics evolves on a finite dimensional object, on an attractor. You're taking a massive number of linear observables on a nonlinear object. And so in that case, DMD can work. And in fact, the 2009 paper showed that.
But you have to have assumptions like periodicity and stuff like that.
So yes, you have to have assumptions. So you're absolutely right that if you have a nonlinear system and you have exactly the same number of observables as the nonlinear system, you cannot capture it. But if you have almost a frame on a nonlinear object, you can still capture it. So in some cases, you don't need to add observables.
No, absolutely, yeah. But if you want to converge strongly to the Koopman operator, you do. So by that I mean that for any observable,
you can't fill out L2 with a bunch of linear.
Yeah, exactly. Right. It's kind of obvious, right? But yeah. Okay. So that's that. Right. So dangers when we discretize. So I've already sort of hinted at that with the Jordan block example, right? So we go from this full spectrum, okay, to our EDMD matrix. Sorry. There are typically two dangers. Okay, so now I'm thinking about what happens. Let's assume I've gone to the infinite data limit. I have the inner products exactly, and I'm increasing the size of this truncation. Again, for those of you who are on the purist side, I need, of course, assumptions about my basis and things like that. We can make everything watertight there. So even as I increase the size of my dictionary, okay, I can miss. I can have too much, right? I can have spurious eigenvalues. In fact, I can have something worse called spectral pollution, which is accumulation points of this set of eigenvalues as n increases that are not in the spectrum. So they're really hard to detect because you change the basis size and you think they're stable, right? You can also miss parts of the spectrum. Okay, so we saw that for the Jordan block, right? I'm missing the circle. So this is called spectral invisibility, or too little. Continuous spectral we'll get onto in the second lecture, and then there's verification. Right? So the thing I want to get across, and this is sort of that in infinite dimensions there are different ways a discretization can converge. So EDMD converges in what's called the strong operator topology. So this means that if you take an observable G, and let's say you take your approximation, this guy will converge to this. Okay. This does not mean the spectral properties converge. Okay, and there's a lot of papers out there that get this wrong. And in my viewpoint, spread a bit of misinformation. Okay, so you have to be very careful. EDMD does not converge if you want to get the spectral properties generically. Of course, there are special cases where it does, but generically it doesn't. Okay, so here's a simple example where it doesn't converge. This, in fact, is the example picked from the first EDMD paper. So I've not cherry-picked a weird example. I've taken the first EDMD example and just shown that it doesn't converge. So here I have the Duffing oscillator. Okay, so it's 2D ODE system. And to get a discrete time system, I'm going to sample the solutions, and I've computed the solutions very accurately using a multi-step method at time steps 0.3. So I now have a discrete time system. There's a parameter here, alpha, which controls the dissipation. If alpha is 0, this is a Hamiltonian system, and the Koopman operator is actually unitary, and you can show that its spectrum is the circle. Okay. And to apply EDMD, I'm going to use the same setup in the original paper. I'm going to use Gaussian radial basis functions. So those are Gaussian bumps placed at different points. So R2 is my state space. I'm picking different points. I actually used k-means clustering to pick a good choice. So I'm doing everything I can to make EDMD work well. And then I'm going to have a ton of sample points, right? This is just to ensure that it doesn't really affect the results. So I'm using random trajectories. And this is the picture I get. So these blue dots are the EDMD eigenvalues. These contours here, so remember we had that pseudo spectrum, the relaxation of the spectrum. Okay, these are the epsilon contours of that, computed using a method I'm going to show you in a few slides' time. Okay, so alpha equals 0, the true spectrum should be the circle. Okay, and you're getting a lot of spurious stuff, which you can detect using this pseudo spectrum. So just to say, this is the pseudo spectrum, not of the EDMD matrix, but of the Koopman operator, or approximation of that. So don't be confused. These eigenvalues aren't incorrect. Now, if I switch on alpha, I have a bit of dissipation. I'm not entirely sure what the spectrum should be in this case. Probably the whole disk. But you still get spurious stuff. So for the discretization level, you can look at these contours and see that these don't have small epsilon. So we go here. So if I actually try and measure this quantity here, it's large for the EDMD approximation. Okay. And then you can track the error, the mean of these epsilon contours over the eigenvalues as the matrix size increases, as you increase the dimension of the subspace. Okay, so you look like you have
this left picture. This is like standard Galecan, I guess, with respect to your Gaussians.
Yeah, this is EDMD, right? With
right.
Yeah.
Okay, and I guess I'm a little surprised that it's not closer to the unit circle.
Why?
Well, I can play around with it much.
So it's
usually it's a little bit I played around with. But you're saying this is representative.
So
this is not a pathological case. This is representative.
Yeah. I mean, so you have a lot of good stuff here, really good stuff.
Yeah, I mean,
but you are not plotting the unit circle. It's not plotting the unit circle.
So there is.
Yeah, but you can see where it is.
I mean, of course, it depends on your system.
Yeah. I didn't play with it very much, but for the little thing I played with in very low dimension, that was giving something in it.
Which
what was it? Standard map or something.
Maybe I can comment.
Yeah, sure. Yeah.
So this is the consequence of working in L2. So if you're actually working in L2, and there are some, ergodic theory papers from way back when that show this, for dissipative systems, you're often going to get the spectrum in the whole unit disk, and this is what EDMD.
So I think I was talking about the non-dissipative.
Anyway, I don't want to.
Sorry.
I think I was talking about the non-dissipative case where alpha is 0.
Yeah, so in that case, you actually get spurious eigenvalues, right, on the inside. And that's because the method itself induces dissipation. And so effectively you have dissipation. It's again going to be kind of the whole unit disk. Now it has some peaks, so it's trying to do something good.
That's actually a nice way of thinking about this. Thinking of going from unitary evolution to nilpotent. Truncation introduces dissipation, not just noise in the approximations of your inner products, but truncation itself. Yeah, thanks, Igor. That's probably a. Hopefully that helps.
Yeah.
Okay. So how are we going to fix this, right? And hopefully I'm not scaring everyone with saying DMD is. DMD is great. I have nothing against. It's just, this converges, but this doesn't mean spectra converge. Okay, so how do we fix this? So we have these two types of inner products. I quite like visualizing things, so I plot them in blocks. You've got blue, 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 green, and you take the adjoint, you get green, blue. Half of the people in the room know what's coming next. What's the missing matrix, right? I'm looking at this picture. Anybody who hasn't seen this before want to guess? Be brave. Sorry? If you're looking at the color scheme, what's the missing combination? Green, green. Yeah. It's not a true question, right? What does green, green correspond to? So this is a quadrature approximation of this inner product. Okay. Why is this useful? Okay. Well, if you're thinking about correlations, right? This is sort of present time. This is future time. Present time. This is future time. Future time. Right? So that's one way of thinking about it. But you can actually connect these to the pseudo spectrum. So remember those epsilon sets. So I'll call this matrix where I take this whole collection here, G, this K1, because I've got one K, and this K2. Now let's take a candidate pseudo eigenfunction. I don't really care how you get that. It could be EDMD, it could be something else. We'll find another way of getting them in a second. And let's suppose you also have a candidate lambda, right? So you run an algorithm, you want to tell how good is this candidate. Or you can look at the squared residual. So that's the epsilon squared. It's just this inner product. You expand using the spaces, okay? And then you take a large data limit, right? And you get this nonlinear pencil, okay? An infinite dimensional residual. So there's no truncation here, other than assuming my initial observable is inside my subspace. Assuming in the large data limit everything converges, I get this nonlinear dependence on lambda, but I can get this from a finite matrix. So by introducing this extra matrix, I can start to do things like clean up EDMD and get rid of the spurious stuff. Okay, so I wanted to go to the blackboard and show you a little bit of maths as to why this is, what's actually going on here. So to do that, what I'm going to do is I'm going to first look at a self-adjoint matrix, or operator, sorry. So if you have a self-adjoint operator on a Hilbert space, you can split up its spectrum into two parts. So there's something called the discrete spectrum. So this is the set of isolated eigenvalues. I apologize for my blackboard handwriting. Set of isolated eigenvalues of finite multiplicity. You'll see why this is important. So the essential spectrum, which doesn't exist in finite dimensions. So let's actually write it like this. This is, so you take the whole spectrum, and you take away the discrete spectrum. Where does this terminology come from? Well, if you look at the map, Z goes to A minus Zi inverse. The discrete spectrum corresponds to the poles of this map, and the essential spectrum, every other singularity. So perhaps not correct to just call it essential singularities, because you might have things like branch cuts and stuff like that, but it's the rest of them. So this is very, very useful. So, okay, so let's suppose I have a self-adjoint operator, and I'm going to, I don't necessarily assume it's bounded, but I assume that it's what's called bounded below. So if this is the real axis, this means that there's a lower bound on the spectrum. Okay, so you might have, for example, in fact, let's color code this. So this is the essential spectrum, and this is the discrete spectrum. You might have a band or something like that. Think of like a Schrodinger operator or something. And then you might have a bunch of discrete eigenvalues. Maybe they accumulate here, maybe there's one gap, and then maybe it's discrete Yeah, right. Now, the classical way of approximating the spectrum of this guy, which goes back to quantum chemistry, is to project onto a subspace. So this is what we're doing with EDMD, right? So this idea of projecting onto a subspace is extremely old. So you take, what am I going to call it? Like some subspace, Vn. So let's say this is on some Hilbert space. Okay, so this is inside the domain of A. Okay, which is a subspace page. I think that's relevant. Okay. You take the subspace, I've got an n because I'm going to increase their size in a second. Okay. You take the subspace, right, and then you have an associated orthogonal projection, okay, and then you look at the operator, let's call it an, okay, which is you take A restricted to this subspace, okay, so that A then maps back into the Hilbert space and projects back down, like what's Pn. Okay, so this is just what EDMD is doing for the Koopman operator replacing A. But of course, the Koopman operator is typically not selfish, right? So there will be a connection in a second, bear with me. So you have this. And then what do the quantum chemists do, right? They say, okay, I'm going to take the eigenvalues of this, right? Let's assume this is n-dimensional. So I have lambda 2 all the way up to lambda n. And to keep track of the space, I have this. Okay, so what does that actually look like? So if I go back to my picture up here, what you'll observe if you do this is that the eigenvalues are always shifted to the right. Okay, so I can call this first eigenvalue of A, not the projected operator, mu1. Let's call this guy mu2, and so on. And then, very importantly, we're going to get stuck at the essential spectrum. Okay, so everything collapses. You can think of the essential spectrum as infinite multiplicity. Everything. Let me just take n goes to, or m goes to infinity. Okay, so you have this collection of eigenvalues, and what happens is a theorem that says, lambda, you take the jth guy of this is greater than or equal to mu j, so that's the true eigenvalue of the operator. And under certain conditions, as I increase the size of this basis, this converges to this. Now, we said we got stuck. So what does this mean? This means that if you take a self-adjoint operator and look at the bottom of the spectrum, you can get it up to the essential spectrum without getting any spurious stuff and without missing any parts of the spectrum. But you can't necessarily go further and get these guys. Now, what on earth does this have to do with ResDMD? Okay, so what you do is you take an operator T now, it need not be self-adjoint, and you want to compute its pseudo-spectrum. Yeah.
Okay. So what is the implication of this in the kind of density functional theory you're
Oh, this is fun. This is how.
That's no, I understand. Yeah, that's exactly how we do the variational blah blah. But the question is, what if you get stuck? What you're gonna miss in terms of description of the
everything above the center.
So you basically lose the free states or something. You are unable to capture.
That's not okay.
Amount states.
So you will still typically approximate these for a finite n, but all of them are still moving to the left, and you can get spectral pollution in these guys. So it's impossible to get spectral visibility for a self-adjoint operator, but everything is still pushing to the left, and actually that pushing to the left is one of the reasons you get spectral pollution.
So yeah, but I think in physical terms, you miss the high energy.
Physical terms, you can get spurious eigenvalues here.
So, but when you look at high energy,
you don't miss them.
Yeah.
But for any fixed index,
yeah,
it'll go down.
Yeah. Okay. Yeah.
Okay. So if we have a general operator, right, we're after singularities of this, we can look at the norm of this, and we can take the reciprocal. This looks scary, okay, but because this doesn't exist on the spectrum, but I can treat this as 0 on the spectrum. And it turns out that there's a very nice formula. So sigma inf, I'll describe in a second. I'm going off on a huge tangent, so please bear with me. But it's one of my favorite things. So please indulge. So sigma inf, what is sigma inf? This is just the analog of the smallest single value. So if I have an operator S, this is the inf of norm of Sx. So X is in the domain of S. X has norm 1. So there's a relationship between pseudo spectra and smaller singular values. You do need this adjoint. So that's an adjoint, typically in infinite dimensions. But for the sake of this talk, let's ignore it.
Why do you need the adjoint?
Because of residual spectrum. Right, I don't really have time to go into it, but we can.
Oh, it's like the ranges.
There's loads of different ways an operator can not be available. Yeah. Okay. So why all of this stuff? Well, here's the trick. Okay, so we're going to apply Rayleigh-Ritz, this method, to this. The issue being that T, think of it as the Koopman operator, is not necessarily self-adjoint, and we don't want to have this issue where we get stuck. Okay. So at the risk of straining everybody's necks, we perhaps should have moved on here. Does that fit? It does. Okay, so here's the trick. Sigma inf T minus I. Now, what is DMD or EDMD implicitly doing? It's shoving the projections. Oh, this is terrible chalk. Right, so you do a squared projection, right? You project into subspace. This doesn't converge, but this guy, where you have a projection only on the right-hand side, does. And you can see that from the definition of the injection modulus. Now, so this converges down is this. So if we can compute this, we can get this, and we can get this, and we can get the pseudo spectrum. How do we get this? We do the one thing everybody in numerical algebra tells us not to do. Whoops. And sorry for the noise. That's an adjoint T minus I. Tn. Okay. Right. This in the middle is self-adjoint. So Pn here, I can apply this picture, and I only care about the bottom of the spectrum because of this shift Z. So I can turn a non-normal spectral problem into a sequence of nice bounded below self-adjoint ones. Now, if we expand this out and we go back to res DMD, that's exactly what we're seeing is that expansion written in the basis. So there's a connection between res DMD and Rayleigh-Ritz. I call this a folded operator. You're sort of fixing a Z as an anchor point, folding the operator over itself. Perhaps Marco will tell me if there's a correct name for. Okay, yeah. Marco is my spectral oracle. If you ever have a spectral problem, chat to Marco. He's the expert.
ChatGPT was the expert these days.
Maybe it stole you, right? It stole your papers and. So that's what's underlying this, right? It's this Rayleigh-Ritz for self-adjoint operators to this folded guy. Okay, so we've not got very long, but I've not got very much left. So you can avoid too much, right? You can avoid spectral pollution, and to do that, you take this residual and you basically truncate to some epsilon. Okay, and then you can prove that this avoids pollution. So here's an explicit algorithm. I'm not going to go through it in gory detail. So actually, one thing I will say is that to compute this residual, this is just a generalized eigenvalue problem. So it's very easy to do on a computer. Okay. Typically, even if you avoid spectral pollution, you might not capture all of the spectrum with the projection, right? So you can actually compute pseudo spectra. Okay. And the way you do that is you search for candidates that minimize, or rather I should say minimize this guy, okay? And you can get a theorem, and again, for those of you who want the rigor, look at the paper, you get error control. So the set that you spit out is a subset of the pseudo spectrum, and that's because of this monotonicity, okay? So you get verification. So with a finite set of basis functions, you can get it. And then you also get convergence. Okay, so here's the picture for Duffings. So this picture is actually taken from a recent paper of Igor and myself that I'll talk about in lecture 3. But essentially, there's a way of, so these epsilons are the pseudospectra computed using ResDMD, and then there's a way of locally shrinking the pseudospectra under certain assumptions that allows you to get a convergent algorithm. Okay, so you can fix ResDMD not converging. One thing I should say as well, you don't need anything extra. You're using exactly the same data, right? And it's a very cheap post-processing step. Okay, so here it is for it's blurry, but for a bunch of other systems. Again, this is taken from our paper. You have different types of systems, different types of basis functions, different types of spectra and pseudospectra. Sometimes EDMD converges. So this goes back to Igor's point about the fluid flow of the cylinder. This is a periodic thing. It's very easy to get. Often it doesn't. Okay, so blue here is EDMD, red is as conversion. Okay, so I want to sort of rush through a few applications. It's been quite theory heavy. Hopefully you enjoyed the digression. So here's one example. So this is a fluid flow simulation on a periodic stack of aerofoils, large Reynolds number, ambient dimension 300,000. And what we're doing here is we're getting these Koopman modes associated with verified pseudo-eigenfunctions. So these are the residuals. Okay? Okay, so you can get these verified spectrum modes. You can also do it to get dictionary verification. So this is a very simple example where I'm comparing a linear dictionary to a non-linear dictionary and plotting this residual to see which does a better job. So you can see, Gary, actually, the dictionary really does matter for getting a good approximation. So it's not just the operator and the diode, the dictionary that you choose. But you can tell after you've done the computation whether it's a good job by taking this error bound. Okay. I'll show Sir Gustav Conradi, who maybe he's not here, but he's done some much better examples of this kind of learning neural networks and kernels and stuff like that by using this residual as a loss function. And you can get much better things like prediction and stuff like that. And finally, often it leads to better compression. Okay, so DMD, when you're projecting onto these POD modes, these pod modes, you're always doing a compression, right? But of course, that's not the same thing as getting an optimal compression according to this residual. So here's a transient dynamical system. So this is my collaborator, Matsuke at Virginia Tech. I actually visited his lab. He has this really cool laser cannon. Felt like I was in Star Wars or something. And you blast some air. Please don't ask me about the fluids. You can email him. And it sends this transient shockwave. Okay, so we had, I think, about 60 realizations of this experiment, and we were trying to build a Koopman way of predicting this transient wave. So we trained this on, I think maybe like half of the data or something, half of the examples, and then we tested it on unseen shockwaves. And what you do is you keep a certain number of the modes, an optimal compression. So the modes you can think of as pseudo-eigenfunctions, kind of. So here's the wave. Okay, here's the start of the wave that the predictor sees, and then everything beyond that point is unseen. If you truncate to 40 modes using an SVD ordering, so that's POD, you get the red guy. Pretty good. If you project according to residual, you get a much better approximation. So POD compression is not always the best thing. You don't always want to minimize the energy loss, particularly for transient dynamical systems, and that's really important. And then you can see that there, exactly. You get a much more efficient compression. Okay, I wanted to leave some time for questions, some pointers. EDMD is a Galerkin method. Simple as that. You're projecting your Koopman operator onto a subspace. DMD is the transpose, if we still got it, I remember that, is the transpose of EDMD with a linear choice of observables. So if you're after an intuitive explanation, EDMD is a bit like a spectral method. DMD happens in physical space, right? So EDMD is in coefficient space, according to your dictionary. DMD is physical space. So it's a bit like spectral versus collocation. but the analogy kind of doesn't really go further. And this is something I wanted to get at, even if it's a bit provocative, because I want to hammer it home. EDMD and DMD generically does not converge to spectra. Okay, so anyone who says it does is either misguided or, more likely, adding very strong assumptions, such as a known finite dimensional Vector subspace. And I wanted also to highlight Eagle's paper here, who I think was one of the first to sort of spot this pollution, or at least write it down properly in a mathematical way. So it's a very nice example of this paper where he's doing it for the doubling map. And you get exactly the same type of phenomenon we had for the shift, but for an exact Cuban operator for a system. Okay, and then finally, you can fix all of this very easily, so you don't have to be afraid. Just apply residue, green, green, right? So if you forget everything else from this talk, green, green. Yeah, on that bombshell, it's probably any questions? Yeah.
And is the coloring correct on the last slide? But the one before this.
Yes, because I was also
The coloring?
the
Like,
coloring
is
for
the
the
red and
relative.
black color on the right flat? Is that
Oh,
what you mean?
no, yeah, sorry, yeah, it's wrong. It's wrong. That must mean it's wrong in the paper as well. That's like. Black is really, black is residual. Thanks for spotting that. Yeah. I never read my papers after this. Any other less embarrassing question? What? Point that out. Yeah.
Just a kind of general question
Yeah.
from the point of view of total ignorance. Are there, I mean, even people working in, say, Schrödinger spectra have kind of lot, 30, 40-year history of tricks for trying to avoid or filter out spectral pollution.
Yeah, these guys, right?
You've mentioned one trick here. Are there other tricks that people working in?
No. And this is exactly one of the reasons we want this workshop, is because there's got to be tons of these kinds of tricks are used in the spectral theory community. There are lots of others, and it'd be really fruitful to sort of transport all of that technology over to Cooper.
This one's really nice and reliable, but it's also expensive.
Yeah,
like something cheap and
you want something like the one where you apply it to the result, right? The difficulty is often for Cooper you don't get this nice picture. So maybe unitary or something. So it's kind of hard to, I don't know, but yeah, that's something we should definitely discuss, is how algorithms and methods that people in the spectral theory community have built can be transported to Cooper. Because that's actually how I first got into Cooper, right? I only got into Cooper like during COVID. I was from the spectral theory community. And then, I was developing these algorithms based on what I'd done for other types of operators. So I think that's something we should definitely talk about. Yeah.
Can I ask also maybe a bit related to that? So in that picture, I mean, the intuition I have is we're mostly interested in the eigenvalues or the spectrum coming from the right, from the largest.
At the bottom. At the bottom of the spectrum.
Yeah. So maybe there's a sign.
So you're thinking like for like transfer operators.
Yeah, exactly. So
So if you invert it and it's bounded above, the same thing happens at the top of the spectrum.
Okay.
For a lot of operators, it's actually quite complicated to characterize when it happens, but you get a similar sort of thing outside the essential spectral radius. But yeah.
So something similar.
So at the end of these lectures, I'll give a reference to my book that's about to come out, and that has a lot of stuff on this thing, so we can chat about that. Yes, please.
This does depend, the performance does depend on the choice of basis function.
What's the
How well you can capture the true spectrum.
Oh, absolutely. Yeah.
So then what's the guide of which?
Right. So one of the things we're moving into is using the residual as a loss function for training bases. So that's something Gustav is doing. It's one of my students. And also George has a reason. So George there in the back of his wave. Oh, sorry, yeah. There are two Georges. George Koo. He has a very nice paper where he's training a neural network with this loss function and getting better results. That's on the archive. So have a chat to George. Yeah.
So about your last provocative statement.
Yeah.
So there are certainly lots of, let's say an open set of maps for which we know that EDMD does converge to, like, many specific, useful basis functions do converge to spectra, which is not the L2 spectrum.
Exactly. Yeah. Yeah.
So maybe you want to say the L2 spectrum then.
Yeah. Yeah. But I'm thinking spectral, whatever helps space and work. But yeah. No, you're absolutely right. So there is a connection that for some systems it doesn't converge to the L2 spectrum, but something else that's meaningful. But yeah. And Caroline and also Julia, they're the people who talked about that. It's really nice, interesting. Well,
I'd also add that DMD with delay variables will converge to the same kinds of things.
to the resonances.
The resonances, which are often spectral. There we go.
Yeah.
They converge to resonances.
It's more memorable to be proposed. Anything else? All right, I guess we'll reconvene whenever the next walk is.
Change the whole